Okay, let's start today's class. But before starting today's class, so I posted the midterm logistics. Sure. This one. Okay. So I posted the midterm exam logistics on the Blackboard, and then as you can see, we will take the midterm exam on November 1st and during the regular class time. But I think the exam time requires so a little bit longer than the usual class time. So I hope we can start earlier than the usual class start time. So actually just focus on this exam hours. So I hope we can start at 1:45 p.m. So usually we start at 2 for the usual class, but for the exam, I hope we have 15-minute longer exam time. So if you have any conflict, then please let me know immediately. Then we will start at 2. Okay, so please let me know immediately if you have any time conflict with the exam time schedule. Okay. Also, as I announced this exam will be the online exam. So you need to prepare. Actually, you need to install Lockdown browser, and then you need to prepare webcam because we will during the exam your environment and your face maybe will be recorded by Lockdown browser. So please, and then also I will post some test quiz that use Lockdown browser before the exam. So you can test how Lockdown browser works before the exam. Okay. Okay. So any questions about the exam? Okay, good. So, okay. So let's go back to today's class. So actually I posted the recorded video for the previous class because we had a substitute holiday on the last Monday. So actually we conclude chapter 2, the instruction set architecture of RISC-V, and we are learning about the arithmetics for computers. So actually in chapter 2, we learned about the instruction set architecture. So that is interface between software and hardware. So I mentioned that the instruction set architecture it's like a protocol or promises between software and hardware. So it's a little bit similar to some software protocol because it's just some interfaces, okay? But from this chapter 3 and chapter 4 and chapter 5, we will learn about the hardware system of computer systems. So hardware architecture of computer systems. So in the chapter 3, we will learn about some detailed hardware engine for arithmetics, okay? So actually in the previous class, that's the recorded video, we learned about some basic arithmetic unit that is used for integer arithmetics, okay? So we learned about addition and subtraction, but as I explained, this addition and subtraction of the binary number is very similar to our normal decimal arithmetics, okay? So actually, we can perform the addition or subtraction for each digit, and then if carries are generated, then this carry will be included in the calculation of next digit, like normal decimal arithmetic, okay? And then subtraction, subtraction is actually the same to the addition, y. Then in the decimal arithmetic, then for the subtraction, we just negate this operand. So it's like 7 plus minus 6. So just negate this operand and then just performs addition. Okay, and then it's the same to the computer hardware. So actually, the addition engine, actually this addition hardware is used for subtract operation. Okay, we can just negate this second operand of the subtraction, and that's it. And then what is important? We need to check the overflow. So what is overflow? The sign bit can be changed for the very large number, or for very small number, like very what's that? It's the very large minus number. Okay, so we can just check the sign bit of the result, and then with the sign bits of 2 operands for this addition or subtraction. So actually, for the signed number operation, we need to check. We need to check the result of the sign bit. Okay, we need to check the overflow. And the multiplication is a little bit complex, a little bit more complex than the addition and subtraction, because actually it's the same to our normal decimal arithmetic, because for the multiplication, we just perform the multiplication operation for each digit, and then we generate the partial product for each digit, and then we just accumulate these generated partial products, and then we make the final result for the multiplication. The same to the binary number, the binary arithmetic. So it's the same actually. So the partial product for each digit of a multiplier is also generated, but the good thing is that this number has only 2 values, 0 or 1. So 0 means 0 will generate the all zeros for the partial product, and then 1 will generate the just same to the multiplicand. Okay, so we can just shift the multiplicand, and then by the location of the digit for this multiplier, and then just generate the partial product. And then these partial products are accumulated, and then to make the final result. And that's it. But its process is more complex than the addition. And then with this very simplified multiplication hardware, this hardware will consume more cycles. So why this cycle number? Why this cycle number? Why is this cycle number important? Because as we learned, so execution time is proportional to the number of cycles. Actually, number of cycles multiplied by TC is the clock period. So that determines the execution time. So in order to increase the performance, we need to reduce the number of cycles. So with this very simple shift and accumulation engine of this hardware multiplier, this multiplier will consume more cycles, then this number will increase if the many multiplications are included in a certain software. Then the execution time will also increase. So how can we increase the performance? We can increase the performance, the number of required cycles for this multiplication. So that's why we can apply the very fast multiplier. So But this is the out of scope of this course, and then you may learn about some digital design of this very simple, not that simple. So you may learn about some digital design for arithmetic engines for computer hardware in maybe in electrical engineering course. Okay, so like it's a topic of digital design course, not this course. So we can apply the very fast multiplier to increase the performance of our computer hardware. Okay, and then also RISC-V supports provides several instructions for multiplication like this. Okay. Then how about the division? Division is also the same. So it's the process of this binary division is also similar to the process of our normal decimal division. So, but division is more complex than the multiplication because division requires what is comparison and subtraction. That is called the conditional subtraction. And it's the same to our normal division, like decimal division. So in order to perform division for our some multi-digit decimal numbers, then we just check the magnitude of dividend and the magnitude of divisor. And then that means, and then if the magnitude of dividend is larger than that of divisor, then we can subtract. So we can subtract the divisor from dividend. And then that's the same to the binary division also. So we need to first check the magnitude of this digit of the dividend and then the magnitude of divisor. And then if this magnitude is larger than the divisor, then we can subtract divisor from dividend. But if not, we just move to the next digit and then also check the magnitude. And then this process is also replicated for each digit of dividend. So actually the very simple divide hardware is very similar to the hardware architecture of multiplication. But one different thing is control of the subtraction. It's a conditional subtraction. So actually in the multiplication, we can generate the partial product of for each digit of multiplier. Well, you may think, oh, it's a multiply the number of a certain digit of a multiplier is 0, then partial product is not generated. You may think like that, but zeros are just generated, and then these zeros can be included in the accumulation without any control. So that means any comparison or any control part. But in the division, we need to first check the magnitude of dividend and the divider, and then based on the result, the subtraction can be performed or not. So that's why the divisor hardware need to include the control part. Okay. Yes. So also we can apply the best divider hardware. So we can also increase the performance of computer hardware. So RISC-V support some instructions for this division, and then we can also use these instructions if the RISC-V processor support divide operation. Okay, so I said if a RISC-V processor supports divide operations. So why do I mention? So we learned that in the chapter 2, the baseline ISA of RISC-V is integer ISA. So actually in this course, we are learning about the robot RV64I here. So that means that this RISC-V processor, so based on the RV64I, just to support some arithmetic instructions like add, sub, and add I, and that's it. The multiplier, the multiplication and division operations are not supported by this baseline RISC-V instruction set. And because, so that means that we don't need to actually for this, if a processor just to support the RISC-V baseline, that means the integer instruction set, then this processor does not include the multiplier, does not need to include multiplier or divider hardware engines, because these instructions are not supported by this type of instruction set. Then how can we run the divide operation or multiply operations with this hardware? How? So we already know that the multiplication or divide operations are frequently used in our programs or applications, but these instructions are not supported by baseline RISC-V processor or baseline RISC-V instruction sets. So how can we use multiply or divide operations? So actually these operations can be translated into the repeated addition or subtractions. Okay, so the compiler can translate these multiplication or divide operations into the multiple additions or subtractions. And then we can, that means that, so these operations will be translated into RISC-V assembly code that use only addition or subtraction instructions. Okay, because the hardware does not support the mul or divide div instructions. The compiler need to generate the some compatible code or compatible some procedures using multiple additions or subtraction instructions. Okay. Okay. Also, we learned about the floating point. So actually, up to this slide, we learned about the integer arithmetic. And then, what is a floating point? The floating point means 소수 in Korean. So actually, these floating point numbers are used for representing real numbers. Okay, real numbers, not including integers. Okay, so it's used for representing real numbers like this. But as we know, we can use the normalized form or not normalized form for real numbers. But floating point, actually for floating point, we only use the normalized form. So floating point numbers represent the normalized real number in the computer systems. So that's just a rule, the rule for representing some number systems. So actually, this is the specification. defined in IEEE standard. So we can just, if we just know the rules for representing these floating point numbers, and then we can just follow the rules, okay? And then the hardware need to be designed based on the defined rules for floating point numbers, okay? So in a C, you can use the float or double data type for the floating point numbers. That is the single precision, that is the double precision floating point numbers. So we learned how the floating numbers can be represented using binary data. So I said this is just a rule. So this rule just define how this normalized floating point binary number can be represented using some data fields of the binary code, okay, like this. So we learned until this slide, okay. So actually this floating point number is important for actually how can I say, as an AI applications or like neural networks or some other type of AI applications, because the AI applications handle very large amount of data. Actually, the AI applications are composed of many linear algebra equations. Like that means the matrix arithmetic. Okay. So, and then as elements of these matrices, we use floating point numbers. But as the number of data, number of elements is very huge, it's very large, then so we may need to reduce the size of floating point numbers. If we reduce some size of that means the number of bits in the floating point number, then what is sacrificed? It's the, oh, not this part. The precision will be sacrificed. So why? So actually for the single precision floating point number, we need 32 bits. Okay. And then for the double precision numbers, we need 64 bits. Okay. But I said, so we thought this 32-bit single precision floating point number and then 64 bits double precision floating point number. So the precision is that for the single precision, the resolution, the smallest resolution that can be represented with the single precision floating point number is approximately 2 to minus 23. It is because this fraction part, the width of a fraction part is 23 bits for the single precision floating point number. Oh, you may think that, oh, it's a very small number, but in decimal number, it's about the 6 decimal digit of precision. That means 0.00000, very similar to this six digit of the decimal precision. Okay. And then for the double, it's approximately 2 minus 52, then there's the 16 decimal digit of precision. Okay. So why do I mention this precision? So I said that the AI application handle very large amount of data. So that means data size can matter in this AI applications. And then in order to reduce the data size, we can reduce the width. That means the size. That means number of bits in numbers. Okay, so instead of using 32-bit single precision floating point number, we can use the 16-bit precision floating point number, or even we can use the 8-bit floating point number. So we can define the number systems. Okay. So if we use the 8-bit floating point number, we can reduce the data size by 1/4. 1/4, because we just used the 8-bit. But what is sacrificed? The precision can be sacrificed. So this is also some research topic in the computer systems and the AI applications. Okay. So we can calculate the precision like this. Then how can we represent the floating point number? So that's just the example. How can we represent the minus 0.75? So if we see the this number, then we can this number is the negative number. So the sign bit is 1, and then the magnitude of this number is minus 0.75. Is the actually the magnitude of 0.75. It's similar to the it's equivalent to the 1.1 multiplied by 1/2. Okay, what is this number? It's 1 point. Actually, what is this number? It's the 1 plus 1/2, because this is the fraction and this is the some. So this is significant and this is the some 1. So the normalized form. So that is the first digit of the significant. So this is just the 1. And then it's multiplied by 1/2. Okay, understand? So actually 2 minus 1. So in the single precision representation, so we can use this single precision floating point representation. So sign bit, and the exponent is here, and then fraction part is here. Oh, what is the fraction part? This is a fraction part. So fractions of this number is 1,0,0,0,0. And then how about the exponent? What is the bias of single precision? So bias of single precision is 127. And then the real exponent of this number is -1. So exponent part will be -1 plus 127. That is the 126. So this is the exponent part of this number. We can just merge sign bit, exponent part, and fraction part to generate this single precision floating point number for minus 0.75. Okay, like this. So for the single precision, the exponent part will have 8 bits. And then for the double precision, the exponent part will have how many bits? I need to check. It's 11 bits. Okay. Then the sign bit is here. The exponent part is here, and then fraction part is here. Okay. And then the reverse process. So we can also translate this floating point number of the computer system to our normal decimal numbers. Okay, like this from this one. So if this number is given, then we can just separate the, this is the sign bit, and then it's a single precision floating point number. So it's a float data type in C. And then this is the exponent part. So exponent part is 0, 1, 1, 1, 1, 1, 1, 0. So it's the 128. And then what is the fraction part? The fraction part is here. So its fraction part is here. So sign bit is 1. So sign is negative. It's a minus sign. And then what is the significance of this number? 1.01, because fraction part is here. It's 1 plus 1/4. Okay, 1.25. And how about the exponent part? It's the 129. So 129 minus bias is 2. So this is the decimal number. It's minus 5.0. And then actually this process is easy, but this process is, so from floating point number to our decimal number is a little bit tricky. And then, but this part is from the floating point number of the computer system to decimal number is easy. Okay, because if we just know the sign part, sign B part, and exponent part, and fraction part, we can easily translate this number to decimal numbers. Okay. Okay. So for the floating point number, if we just know the rules, that's just the specification, then we can translate the floating point numbers to decimal number, or decimal real number to floating point number. It's just a rule. Okay. Then let's learn about denormal numbers. So denormal numbers mean that it's not normal numbers. Okay. So actually, normal numbers can be represented using this floating point specification, it's a definition rule. But the computer hardware just use these denormal number forms to represent some special numbers or not a number. Okay. The first type of denormal number is if the all exponent bits are zeros, then this number is used for representing very small numbers. That means that the magnitude of this number is very small. Okay, the magnitude, because it's like because of this sign bit. Okay, so that means 0 is here, and then 1 is here, minus 1 is here, and then plus 1 is here. And then if the all exponent bits are zeros, then this number is used for representing these very small numbers. So that means that the numbers that have very small magnitude. Okay. Okay. So if the all exponent bits are 0, then that means here sign bit is the same, and then we just use the 0, the first number of significant. So usually we use 1 because, and then the fraction part is added to the 0, and then the exponent will be minus bias plus 1. Okay. If all exponents are zeros. It's a little bit different, okay? So if you see the normal representation of the floating point number, the equation looks like this, okay? But if the all exponents are zero, then it's a little bit different, okay? So it is used for representing smaller than normal numbers. And then if the all fractions are zero and all exponents are zero, that means it's if all fractions are zero, all fraction bits are zeros, then that means zero. Okay, oh, that means all exponent bits are zero and all fraction bits are zeros. Okay, so that means these fraction parts are zero. Okay, and then so it's zero, just zero. Okay. So if the exponent is not zeros, that means 1 plus, and then if all fraction bits are zero, then it should be 1 plus 0 multiplied by 2 minus some exponent. So it's not zero, okay? But if all exponents bits are zeros and then all fraction bits are zero, then the equation becomes the 0 plus fraction, but fraction also is a 0. That means that represents the 0 for floating point or double data type. Okay. So there are two representations for 0.0. So even though the sign bit is 1, then that means the minus 0.0, and then if the sign bit is 0, that means plus 0.0. So both these are all 0. Okay. So if all fraction bits are zeros and then all exponent bits are zeros, that is 0 for floating point numbers. Okay. Okay, and then let's see some special numbers in the floating point representation. And then if the all exponent bits are ones and then fraction bits are zeros, all fraction bits are zeros, that means it's infinity. It's a very large number. Okay. And then it's just a rule. So, so it's just definition defined in the IEEE standard. And then all exponent bits are ones and all fraction bits are not zeros, then that is used for representing NaN. That means not a number. That's not a number. Okay. So sometimes if the computer systems cannot generate a normal number from operands. So like divide by zeros, okay? 0 divided by zeros. So undefined results are generated from a certain instructions, then computer systems can just return not a number. This is not a number, okay? NaN. So I believe you can frequently see NaN character in Excel. Sometimes you can you can see not a number result from Excel. Okay, so that is the return number is from the Excel application is not a number. So in a floating point number system, if all exponents are ones and then all fraction bits are zeros, then it is used for representing not a number. Sometimes it's called NaN. Okay, not a number. Okay. So these are some special numbers represented by floating point number systems. Okay, then let's see how the floating point arithmetic can be performed in the computer systems. Okay, we can start from our normal decimal arithmetic for the floating point numbers. Okay, so this is an example of floating point addition. So like 9.999 multiply with 10 to 1 and then blah, blah, blah. Okay, this is the example arithmetic operation in our normal world. So that means the decimal numbers. How can we calculate this operation? Okay. So first we need to align decimal points. So these are the normalized numbers, right? So, and then as you know, the exponents are different. So the first thing we need to do is aligning decimal points like this. Okay, the shift numbers with a smaller exponent. Okay, and then we can add the significand because this part is the same, so we can get some result. But as you can see, the result number is not normalized. It's not a normalized number. Why? Oh, this significand has 2 digits. Normalized number means that the significand has only 1 digit on the left side of the point, decimal point. Okay, so but this result has 2 digits, so it should be normalized. And then it's easy for the decimal numbers. Okay, you can just move the decimal points, and then the exponent is updated. Well, as you can see, this normal significand has 4 decimal digits after the decimal point. So we may need to adjust the decimal point, number of digits after the decimal point, like this. So these are the process, the arithmetic operation for decimal numbers. Okay. How about the binary numbers? So binary floating point numbers. It's same. As you can see, the process of floating point arithmetic is same. The first align binary points. So, and then we just set the same exponent for these 2 numbers, and then add significand, and then normalize, and then round. Okay, if necessary, round. Okay. So these are the required process for the floating point addition. So what is different? Actually, for the integer addition, the hardware is very simple. You can just design very simple addition engine for the integer addition or subtractions. But not to apply floating point arithmetic, so floating point addition, then we need to flow these 4 processes like these 4 steps of floating point additions, okay? Like aligning, add significant, normalization, and round up or round down. So these operations are required. So that means the floating point addition require very complex compared to the integer addition or integer subtractions. Okay, integer addition engine or integer actually subtraction is addition engine. Okay, so floating point addition is much more complex than integer addition hardware. Okay, and then it will take longer cycles. That's why the floating point arithmetic engine requires the very complex structure, and these floating point arithmetic operations, the computer systems require more cycles. So it's a longer execution time. Okay. So these are some simplified hardware structure of floating point adder. Okay. Like this first step, second step, third step, and fourth step. And then each step, these operations or these processes are performed by each step. How about the multiplication? So actually for the floating point multiplication, we can just divide the significant part and exponent part. Okay. For the decimal numbers, how can we perform floating point multiplication? So first, just add exponent part like here. So we just divide the significant part and exponent part, and then we perform the addition for the exponent part, and then multiply significant. Okay, so this is a result of floating point multiplication, but this result is not normalized. So we need to normalize here, and then round up or round down here, and then how about the sign? The sign is determined by the sign bits of 2 operands. Okay. So compared to floating point addition, the required processes for floating point multiplication is similar. Okay. Actually, this part, actually we just divide the significant part and exponent part for the 2 operands, and then just performs the addition and multiplication. Okay. Then this process is the same. So normalization, and then round up and round down. And then sign bit, it's just plus plus is plus, minus minus is plus, plus minus is minus. Okay. It's a very simple exclusive OR operation. And that's it. So required processes for floating point multiplication is similar to the required steps for floating point addition. So that means the hardware complexity of floating point multiplication can be similar to that of floating point addition. So with the binary number is the same. Add exponent, multiply significant, normalization, and then round up, round down, and sign is determined. Same processes. Actually, even though the number systems are different in between normal world and computer hardware, but the required processes, some required processes or required steps for arithmetic operations are very, very similar. Okay. So we can know that the complexity of the floating point multiplier is similar to the floating point adder. So usually, when we design the computer hardware, we just design the integer part arithmetic engines like adder and multiplier and divider. So if we just compare the complexity of integer adder and multiplier divider, then complexity of multiplier integer multiplier and divider are higher than the complexity of integer adder. And then if we just compare the floating point arithmetic units like floating point adder and then floating point multiplier or divider, actually the complexity of the floating point adder and multiplier divider is nearly same. So very similar. But if we just compare the complexity of integer engine and the floating point engines, then the complexity of the floating point engine is much higher. So that means the hardware structure is more complex, and then it will take more cycles. Okay, that's why floating point data is heavy burdens for computer systems. Okay, because of hardware complexity. So actually, if a software engineer does not consider about the hardware complexity for their data type, then the software engineers may think that, oh, we just declare the floating point data type, or more precise data, we can use the double data type for very large amount of data. Then we can use this data for some applications. In the software side, software's view, the computer hardware is just like if data is given, and then instructions are given for some multiply or divide or add, and then results are generated. But what is missing? Time is missing. This time is determined by complexity of hardware engines. Okay. So actually, if we use the float or double data type, or if we use integer data type, and if the integer data type is used, then the performance will be higher. And that's obvious because the required hardware complexity for this integer arithmetic is much simpler. But if we just use the large amount of floating point numbers or floating point data, so we may think that, oh, just a very simple arithmetic, but data type is just different, but the performance can be degraded. Okay, because of complexity, hardware complexity. Why is this important? Modern applications handle a large amount of data. So it's called big data. So we frequently use big data applications. That means that the amount of data handled by computer systems is very large. That's it. But why is it critical? So if we just handle a very large amount of floating point data, then that's heavy burdens for computer systems or computer hardware. And we need to study how to reduce this performance burdens or performance overhead by larger amount of floating point data in our applications because of hardware complexity. Okay. That's why we are learning about the computer hardware architecture. Okay. So in order to support the floating point data, the RISC-V processor provides the separated floating point registers. Okay. So in chapter 2, we learned that the RISC-V provides 32 general purpose registers. So actually, that means that this is the integer register 5. Okay? Integer registers. What does that mean? So actually in chapter 2, also we learned about the integer type instructions. That's the baseline instruction set in RISC-V. So its integer register files are handled by integer instructions. We learned in chapter 2. Additionally, if the RISC-V processor supports the floating point instructions, okay, then this processor needs to provide the 32 floating point registers. Okay, and then the name of this floating point register is called the F0 to F31. How about the general purpose registers X0 to X31? The floating point is F0 to F31. Okay, so the width of the floating point register is 64-bit. Okay, that means RISC-V floating point instructions support the double precision floating point data, 64-bit. And then for the single precision data, we just store the lower 30 bits of register file. Okay, so these floating point registers just store the floating point numbers. Okay, and then these registers are just handled by floating point instructions like fadd, fmov, fdiv. Also, these floating point registers should be accessed by memory instructions. So that means that the memory instructions need to move floating point data in main memory to floating point registers like here, and then also reverse direction. So in order to support this data movement, RISC-V also provides floating point load and floating point store instructions. So if we add F before the instruction name, then that means it's the floating point load or floating point stores. Okay. So these are the floating point instructions supported by RISC-V. So these are the exemplar floating point instructions for RISC-V in RISC-V. So we can just add F before the instruction name, and then also we can add the postfix to represent the precision of floating point numbers. So if you see that this f add.s, so f is here, that means that this is the floating point add instruction. And then after the dot, we can, the postfix S is included. So that means that this floating point add handles the single precision floating point numbers. Okay. And if we add D as the postfix, then that means that it's the double precision floating point instructions. Okay, the double precision floating point numbers are handled by these instructions. Okay, so this is the example. Okay, so we can the instructions for comparisons are also provided for in RISC-V, and then also we can the branch instruction, the conditional branch instructions are provide for floating point instructions. Okay, so these are the floating point instructions. So this is the example assembly code of the RISC-V that handles the floating point numbers. So as you can see, this is a function like F to C, and then it receives floating point argument, a floating point argument, FAHR, and then returns this result of this equation. So this is the compiled floating point instructions of RISC-V. Okay, so as you can see, floating point load instruction is used. It's just to ignore the const 5 or const 9. This is some specialized instruction. And then, as you can see, we use the FDIV instruction. So, as you can see, this floating point load handles the floating point registers. Okay, so like here, so floating point registers are just handled. The floating point load, and then present these other floating point instructions, and then return. So these are just example. So we can, if the RISC-V processor supports floating point instructions, then we can use floating point instructions in RISC-V. Okay. If not, if these floating point instructions are not supported by hardware, then compiler need to convert these operations using integer instructions. What's the problem? So it will include many integer instructions because it's very complex to handle floating point numbers using integer instructions. So performance will be very slow. Okay. Performance will be very low. So we can use high and low for performance, and then for the speed, we can say, oh, it's fast and slow. Sorry. Okay. Okay, so actually, IEEE standard 754 defines the many other aspects of floating point numbers, like additional precision definition or additional round rules, and these are also defined in this IEEE standard 754. Okay, but these all standards are not supported by hardware. Okay, but sometimes we apply to some more simplified hardware engines to handle the floating point numbers. But usually some common parts, like a very critical part of the specification, is supported by all type of hardware. Okay, but the hardware does not support the all things defined by IEEE standard 754. Okay, it's just an optional definition. Okay, some very mandatory specifications are supported by hardware. So actually, this subword parallelism is just a very okay. So I think so I will skip this slide because we will handle this subword parallelism in chapter 6 again. Okay. So actually, this technique is frequently used for graphics processing unit, GPU. Okay, so I will skip this slide. Okay, let's see about some frequent mistakes for some number systems. Okay. Okay. Actually, in chapter 2, we learned that we can apply shift operations for divide by power of 2 or multiply by power of 2. But we need to apply these shift operations very carefully. Why? So for example, if we can apply right shift for divide by 2 power of 2. Okay, and we already know that if we divide some numbers with 4, then it's same to the right shift 2. But it's only applicable for unsigned numbers. Why? What is the result of 5 divided by 4? It's 1. Okay, the quotient of this 5 divided by 4 is 1. What is 5? 1 on 1. And then right shift by 2 is here, just 1. So it's just correct. How about minus 5 divided by 4? It should be minus 1. But if we just use shift operations for right shift operation, like right shift by 2, what is the result? It's minus 2, not minus 1. So that's the problem. We cannot apply right shift operation for unsigned number. So right shift operation cannot replace divide operation, divide by power of 2, if the number is unsigned number. Okay. So the result can be different. And then, so another mistake may be caused by associativity, but a very large number or very small number. So we already know that the x plus y plus z is x plus y plus z. So this is some associativity is supported, so not supported. So this is the associativity rule for the addition. Okay, and then we know that it's obviously true, but computer systems. So how for these equations of x plus, so x plus y is firstly computed, and then this result of x plus y is added by z. How about this? So y plus z is firstly computed, and then x is added to the y plus z. And then how about this? The x is minus very the magnitude is very large, it's a minus this number. And then y is also, the magnitude is a very large number, and then but it's a plus number. But just the sign of these numbers are different, but it's the same magnitude, but it's a very large number. How about g? Z is just 1.0. If we first compute the x plus y, then it will generate the 0. And then 0 plus 1 is 1.0. How about this? 1 plus very large number will generate this number. And then it's just the same number because we cannot express the 1.0 with the precision of this floating point number. Okay. If we normalize the result of 1.5, like this very large number with just 1, then it will generate the actually same number because this number is very large. And then if we just performs the minus 1.5 plus 1.5 is a very large number, then it will generate 0. What is the problem? So what's the problem? Depending on the order of computation, the result can be different. And then this different result can be caused by the normalization or precision of the number systems. Okay. So in reality, with the normal or decimal numbers, the associativity is if these equations are the same, so these two equations need to generate the same result, but in the computer systems, they can be different. Okay. And then floating point accuracy can be also very critical. So actually, the most famous bug in the computer CPU is the floating point division bug found in Intel Pentium. So if you are interested, then you can find these articles, the Intel Pentium division bug. Okay. So it's the end of the chapter 3. So it's a very short chapter. So in the chapter 3, we learned about the number systems in computer hardware, and then how the computer hardware can be designed for integer arithmetic operations. And then we also learned about the floating point number systems. So actually, so the important topic in this chapter is the floating point number systems. Okay, and then also in chapter 3, we learned that the computer hardware, the arithmetic, the hardware complexity of arithmetic engine can be different. In the software side view, this arithmetic engine just generates the result from two operands, but in the hardware side, we need to consider the complexity of hardware. Why? This complexity of hardware determines the performance of entire computer systems. Okay, that's what we learned in chapter 3. Okay, and then this is the end of chapter 3. It's a very short chapter. So I also posted the second homework assignment for chapter 2 and chapter 3. Okay. And then the next class, we will learn about the processor hardware architecture. It's also very important topic in this course. So actually, it's a very important topic. So we will learn about the hardware architecture of very simple RISC-V computer processor. Okay. Okay. So I will stop here. And any questions? 어떻게 생각하나요? So what do you think about, guys? Is it okay or not? So actually, when I posted those homework, then I usually give 10 days until the maybe get right maybe. Okay, so I will consider that issue. Okay, I will consider. Okay, thank you for your attention and see you in the next class. Bye.